Hello everyone, welcome back to my channel. So today we are going to discuss a new paper called Confidence Estimation for Attention Based Sequence to Sequence Models for Speech Recognition. This paper was accepted to ICASP 2021 and I think soon they are going to present this paper at this conference, and this paper is coming from collaboration between Cambridge and Google. So the tutorial, the overview of the tutorial will be first the introduction, then we'll cover something called confidence estimation module, also known as CEM. Then we'll see some experiments and results, and finally I'll show you my implementation, PyTorch implementation of this paper. So what is confidence estimation and why do we need? Confidence estimations or confidence score extractions is one of the very important thing in machine learning, and usually when we ask for confidence filtering, confidence scores from let's say a classification system, so you usually just take the probability of the predictions or the predictions scores, right? But in case of speech recognition we can also do that, but the estimates are not so accurate. So why do we need confidence? How confidence filtering or confidence estimation works in case of speech recognition is, let's say if I give you an audio, the job of any ASR system is to take this audio and to give some sequence of words which are spoken in this utterance, right? Let's say hello world. Now you can ask a question, okay, how confident is the model when it predicts these two words, right? And if the ground truth or if the actual speech when we spoke is hello world, then the confidence should be very high, let's say 0.9 or 0.99 and 0.99, right? These are word level confidences, and getting these confidence scores from speech recognition model is very easy in case of hybrid systems or classical speech recognition systems which use TDNN HMM or GMM HMM models, where you can construct a lattice, and the lattice will be some sort of a search graph. It will be some FST, and this search graph will have some nodes which corresponds to the phonemes, and then you can create something called a CLG graph which will give you the word boundaries, and from the word boundaries you can extract using the word boundaries you can extract the posterior probability of that word sequence. Basically you just take the posterior probability of the acoustic frames, and that will give you the confidence of that particular word, right? So this way there is a very nice way to extract confidence scores from GMM HMM models or DNN HMM models in KLD, and this is very easy. So but in case of end-to-end models, the system seems to be overconfident about the predictions they are making. For example, when you use the end-to-end model, so we will be having some encoder and a decoder. So the encoder job is to take some audio and process it and get some high level representation that will go into the decoder, and the decoder, using some sort of a autoregressive way, it is going to decode this feature sequence into some sequence of words, or let's say subwords, in case of if you are using subword modeling, right? And when you see the confidence scores of these words, so when I say confidence score, you just take the probability of this word, and the probability of this word is, let's say, 0.99. Then you know that the confidence is very high, so that you think that the word is actually what the model has predicted, right? So taking just the probabilities of the words or probability of the subwords directly from the autoregressive model is not so good, because it will be it is most of the time it is overconfident about its predictions, right? Even if the predictions are wrong, it will give you a high confidence number or high probability of that particular subword. This is not so good. So we need some other mechanism to estimate these confidence scores separately, and this paper proposes this confidence estimation module which is put on top of an pre-trained end-to-end ASR model, and then we can train this CEM module, and I'll show you how this training can be done and what is the procedure and so on. And once you train it, this will be very useful to estimate the confidence, and this will be more accurate than just getting the probabilities of the subwords or probability of the letter sequence. So like I said, I will explain you the details of the module, and the experiments from this paper show that they can avoid or mitigate these overconfidence problems which I just explained to you, and they can produce a good confidence scores which are reasonable, and and also they show that even without language model fusion you can get this very good confidence scores. I'm going to show you the results in the end, and we'll see some more results, some other tasks used for some other tasks and so on, and so that is the introduction of this paper. Let's go and see how this confidence estimation module works. This is how the confidence estimation module looks. Assume you have a sequence-to-sequence model, and assume you have trained the end-to-end sequence-to-sequence model, and it will have some encoder, it will have some decoder, and some attention block. Does not need to be you don't have to have the exact same architecture. If you are using transformers, this will not be there. You may have just encoder and decoder, and even for the implementation, I have taken transformer module instead of this LSTM based end-to-end ASR module, and in that case the architecture will vary a little bit. I'm going to explain you that in the implementation section. But for the time sake, you just assume your architecture is a LSTM based end-to-end model, and it will have some attention during decoding, so it's a listen, attend, and spell implementation, for example, right? So in that case, like I said, you have to first train your ASR model using this architecture, and your output should be subwords. The decoder or the output should be sequence of subwords, and for subword you can use any word piece model. For example, you can use sentence piece library and get a vocabulary of, let's say, 10,000 subwords, and use those vocabularies as the output, right? And in this paper they don't have experiments to show how what should be the length of the subword, or what is the effect of number of subwords on the system accuracy, but I think that will be one of the good experiment if they can conduct it. But since the paper is already accepted, so assume you are given particular number of subwords in the decoder, and you train the model end to end for some speech recognition task using some data set, in this case LibriSpeech, and then you freeze this model, right? So you freeze the encoder, freeze the decoder, and what you can do now is you have to train something called confidence estimation module on top of this ASR, and all the time you have to assume this model is frozen. You give an input which is an input x1 xl, which is sequence of frames of an audio. It goes through the encoder, gives you some high level representations, encoder output A1, E2, EL. Does not have to be L if you are using if you can do some sort of projection in between the LSTM layer, this dimension will reduce, but in this case they are just assuming L outputs. Now this will go to the decoder. So the decoder, as you know, in listen, attend, and spell, it will have some attention and gets you some context vector, and that will be used as input to this fully connected layer, and the decoder, and that AT attention vector will also go as input to the decoder and gives you the pre-softmax vector, which can also be used as input to the fully connected layer. Then the model, the ASR model, will predict some output, and the output is yt, yt is the subword at time t, and you can use the embedding vector for that subword from the encoder, because the encoder, in the input encoder, that will have some embedding layer, and you can feed that to the embedding layer and you will get the output yt. So now you have three vectors. You can just concatenate all the three vectors and then use it as input to the FC layer, and the FC layer output will go to the sigmoid layer, and sigmoid layer will predict whether the confidence of this subword is 1 or 0, right? How do we know the ground truth? I'll explain it to you later, but assume you have the ground truths for each and every word, each and every predicted word, and then you can just feed those to you can then do the back propagation through this confidence estimation module, using back propagation, and then train this model, train only this confidence estimation. So whatever I just explained to you in the equation form, it is like this. You have encoder and you feed your spectrogram as input, you get some embedding or higher level representations, which are the encoder output. Then you use the encoder output and the previous attention and the previous prediction, which is D, yes, D, and then you get at a current times attention vector, and the current time attention vector will go as input to the decoder along with some previous prediction, and then the embedding of the previous prediction. Then you apply a softmax and you get the current prediction Yt, and this Yt is put to embedding, and then the dt along with At will go into the sigma, the FC layer, which is the fully connected layer. After that, it will go to a sigmoid layer to predict 1 or 0. Sigmoid like this, sorry, like this. It will be between 0 and 1. It is just a score between 0 and 1, and that score is the confidence of that particular subword Yt. Right. Now, dt is not the previous word. Dt is this pre-softmax vector, which is shown here. Right. And Yt is actually the subword, and Tt is the pre-softmax vector, and At is the attention vector. Now this Pt is the score at particular at a time step t, and for that for the prediction Yt, Yt is your subword predicted at time t. Now the question is, how are we going to train this this confidence estimation module? Is you are predicting some confidences for each and every subword, but you don't know the ground truth of these sequence of subwords, or the actual predictions for our actual outputs for this input, so that you can backpropagate through this. But there is one problem. The problem is, let's assume you have your input x, right, and x is some audio, and you get the y's. Y's will be a sequence of subwords, and let's say you get 40 of them, right? So for input x, you are getting y is equal to some 40 subwords, but the ground truth subwords for this input, let's call this as y star, and this y, let's say it will be 45 subwords, right? So there is a difference. Now we can't exactly map these two sequences. So if there is a one-to-one map, let's say for example, if y star and y both are 40, you could simply say, okay, wherever there is a match, like when the prediction at 0 is same as 0 at y, then I will make this as 0. If it is different, then I will write it as 1. If it is same, I'll write it as 0. If it is same, I'll write it as 1. If it is wrong, it is write it as 0, 1, 0, and so on, so on. So basically, when there is mismatch, you have to have a 0. When there is a match, you have to have 1, right? So this way, you get sequence of ones and zeros, right? This you can take it as output, but the lengths of y star and y will not be same always. So you have to use some sort of a alignment. So you can use Levenshtein distance alignment, and the Levenshtein distance alignment will align these two, and then you can take these ones and zeros, and then this will be taken as the ground truth, and this prediction will be taken as the output or the target. This is the target, this is the input, and then you can use a binary cross entropy loss function like this, and then compute the loss and do the backpropagation. So here you can clearly see C is your ground truth, which is estimated using Levenshtein distance alignment. If it is match, it's 1. If the prediction is wrong, then it is 0, right? So that way your C will be sequence of ones and zeros. Your prediction P, this P will be again sequence of numbers between 0 and 1, because these are passed through sigmoid, and sigmoid will give you any number between 0 and 1, nothing else. So so that way these are actually can be considered as the confidences of those subwords, right? So that is the overall picture of this paper. So basically, you have a ASR model, you freeze it, you feed your input, and then get sequence of predictions, and also make sure you store your D's and A's, and then use them as input to your confidence estimation module. Also remember that during decoding you can get different variants of this sequence of y's, right? Because you can simply use some sort of a beam search algorithm with beam size, let's say, because it's a search, right? So when you get some output from the softmax layer on the for the ASR, you can use any decoding algorithm. So the decoding, if you use let's say beam search, and if you set beam size to 20, so you get 20 different variations of that particular output, right? So that you can also use all of them as input, or you can use all of them to train your confidence estimation model. That will be more accurate. So keep that in mind. So when I'm explaining you the code, I'll show you the beam size and so on, right? So this is the idea of the paper. Now let's look at some of the experiments. For the experiment, as I said, they have used the clean 100 hours of LibreSpeech data, and for features they are using 8-dimensional filter banks with delta and double delta, but in my case I'm not using these two. And for word piece they are using 16,000 word pieces. So this way you will see bigger words. If you use less number of subwords, most of them will be very, very small. And also the subwords, which the number of subwords I am using in this implementation is just 5,000. Now for the ASR module, ASR models architecture, they are using initial 2-layer convolution with max pooling and followed by 4-layer of by LSTM layer. And for the decoder they are using 2 layers of unidirectional LSTM, and the total number of parameters are 184 million. For optimization they are using Adam with learning rate this and batch size 512, and training they are using 5 different regularization method. I'm going to show you in the result section. Label smoothing, Gaussian weight noise with 0 mean and standard deviation, and then spec augment with these parameters, and then they are using exponential moving average, so on. So for evaluation you can simply use some sort of accuracy measurement like precision and recall, but I think normalized cross entropy is one of the very well known, or it's a one metric which makes sense, which we should use here for the for the confidence estimation. So this normalized cross entropy equation looks like this. So you have the C is the ground truth and P is your prediction. So you compute the entropy and then you compute the cross entropy between the prediction and the ground truth, and then you normalize it with the entropy of the original target sequence, like I said here. And this number will be, if it is close to 1, that means you have perfect confidence numbers. If it is minus, you are not so good, right? And precision and recall, like it's standard measurements. Let's look at some of the baseline results. So for the baseline, if you don't use any confidence estimation, if you simply take out the probabilities of every p subwords as your confidence numbers, then your WR will be really good, even if you don't use the the regularization methods like this, your confidence is still good. So you have good AUC, which is the area under the curve, and then you have NCE, which is the normalized cross entropy, but it is negative. As you can see, it's not so great, right? So when you use these regularization method, the NCE will go up, because it is negative here, will go up a little bit, and then your area under the curve actually reduces if you add these things. And so this is just the baseline module. We have to see, once we add the CEM module, what happens. So adding CEM, as you can see here, so the confidence estimation module will actually improve AUC, and also you will get positive NCE. And positive NCE means you are good, you are doing good with the confidence estimations. And you can do it at token level and you can do it at word level, and for both of them it's really good, looks really good. And for the precision and recall, you can see the graph here, that's the confidence scores for the tokens. And coming to another table where what happens when you fuse the language model and see and fine tune the confidence estimation module, the results are not so great when you add language model. In fact, without language model, the NC is uh, better than with language model, as you can see here. But obviously the word errate goes down, which is a good sign. But in case of AAC goes up, but NC is not so. NC is actually a little better when you don't use language model. And yeah, that's all about the theory part of it. Now we can just look at the code, the implementation, which is available in this repo. I will show you. I have so the repo link is this. You can just go to this repo and clone the repo. But before that, I am going to explain it to you, like how the code looks and what it does. So before explaining, one thing is assuming I'm going to this code just assumes you have your output or the ASR pre-trained model already with you, and once you have the pre-trained model, you can use you can extract the alignments or the embeddings from the ASR model for every input from your LibreSpace data, and then store them and so that you can do the training. So as a matter of fact, what I have done is I have used a pre-trained, I have trained a model with these specifications, and then for every input or for every audio from LibreSpeech, both for train and dev, I have extracted these the embeddings. The embeddings, when I mean the DT, AT, and the softmax YTs and so on, and then I have also aligned them using alignment code, which it's here. So this alignment code basically given two words. Word means sequence of two sequence of subwords. It aligns them, and then you get when you align them, you get sequence of ones and zeros, and those sequence of ones and zero can be used as the label when you are computing the loss. I'm going to show you how it is done. You are doing some import, and this is the confidence module. So for the confidence module, I am using some linear layer. So in the paper, I think they say one layer. I'm using two layers here. You have 1024 dimension output from the ASR module. These are the embedding sizes. Also to note that I am not using exactly the listen, attend, and spell architecture. I am just using the transformer architecture, and so the 1024 is the after you concatenate all the DT and YT and so on, you will get this dimension. Then you do the projection to some other dimension, and you then finally project it to one dimension, because this is where you apply sigmoid and get the confidence number between 0 and 1, right? As simple as that. This is the module. This is very simple. And then you have the speech generator, which is a standard data generator or data loader you need. Very simple, most simple one. And then you have this normalized cross entropy function, which is the loss, which is basically the metric which is used to measure the performance of the system. Like I said, normalized cross entropy is the difference between the entropy of the targets minus entropy of the just one second, I think I'll have to show you the equation. Okay, so sorry about this equation here. I think it's supposed to be HC minus HC comma P. So but in this code I have written it as P, so this should be C, then everything is fine. So first you compute the HC, and then you HC is basically the entropy of the correct sequence or the target sequence. Then you compute the binary cross entropy between the predicted sequence and the target sequence. Then you compute the NCE by just taking the difference between the entropy minus cross entropy divided by the entropy, right? So simple, right? So this is the normalized cross entropy equation. Then then after this everything is simple. You just have to train the model. So I have the data, aligned data, some folders. I'm going to upload it to the drives so that you can take it and experiment yourself. This is for the train 100 hours, and this is for the train test clean. And you just mention number of epochs and so on, batch size. Then you create the data loaders for training and testing. And then these are some device, and also these are for the CUDA using training on the GPUs. I think this is repetitive, probably not really. So you use these as optimizers and so on, Adam optimizer and loss function, and then you can just call the training for loop, which is going to take, it's going to run for let's say number of epochs, and it takes the features and labels here are ones and zeros like I mentioned. And then you do the prediction. Predictions will be a sequence of numbers between 0 and 1. Then you compute the loss, then you do back propagation, then you take the optimizer, run the optimizer. Then you can also compute the normalized cross entropy, and this when you run this loop, this is going to train for 10 epoch, let's say. Then if the model is converged, you can do the evaluation and find out the actual test density loss, right? So for the alignment code, like I said, I am, instead of Levenshtein distance, I'm using Wagner-Fisher distance. This is something called backtracking. It's like if you know about dynamic programming or one-pass dynamic programming algorithms, or even Viterbi, you can understand this very easily. So assume there's some this is the alignment code, which will take sequence of two numbers. Sorry, it takes two sequences. One is the one is the predicted subwords, and another is the ground truth subwords, and then gives you the alignment between those two. And once you run this code, the training will be done. You can estimate the NCE loss, and you can estimate the I have not implemented the precision recall, but that is like very easy. But if you want to try this code and test it yourself with your ASR module, I think this is a good start. So yeah, that's about it. That's about the tutorial. Thank you so much for watching this tutorial. If you have any question regarding the code, or if you have any question regarding the tutorials or the paper, you just put a comment, write it in the comment section. I will see, and I'll try to answer it. And that's all for this tutorial. Thank you so much for watching this tutorial. As I said, if you have any question, please feel free to contact me. Thank you.